Good afternoon, and welcome to AIST's Decarbonization webinar series. My name is Charlie Bender, and I'm a staff engineer with the Association of Iron and Steel Technology. Our topic today is the Green Steel Revolution, and this presentation is put on by AIST's Decarbonization Subcommittee. A couple of background information. All attendees' audio has been disabled, and questions to our presenters should be submitted through the Q&A feature, which you'll find at the bottom of the screen of this software. Our host and moderators will continue and determine which questions are presented to our presenter, and the session is being recorded and will be available for everyone on demand at AIST's website. Photos or recording of this presentation is prohibited. AIST's antitrust guidelines include these statements, and basically we're trying to avoid a competitive situation and antitrust problems. AIST also has an anti-harassment policy, which is familiar for those members who have seen or visited AIST functions in the last 3 years. Again, we ask that everyone in the audience participate by putting questions and answers through the Q&A button. We will track each of the questions submitted. Some may be answered live. All will be presented to Dr. Sarah Hornby for follow-up in the future. If you experience technical difficulties in signing into this webinar live, please email training@aist.org for assistance. Our decarbonization series will be discussed quickly by our Vice Chair, Felix Fischbach, who's joining us from Germany. Felix?
Thank you. Thank you, Charlie, and good afternoon, good evening, or good morning to everybody out there. So this webinar is organized by the Decarbonization Subcommittee, which is a committee below Energies and Utilities, the technical committee of IST. We established since 2021. And with this webinar and previous ones, we try to discover topics and unveil a little bit more below the surface regarding decarbonization, what is happening today. This is, if I'm not mistaken, this is the 10th webinar now. And just a short word of advertisement. So the next one will be on 19th of March. This one will have the topic challenges around synthetic hot metal coming from smelters. Here our speakers are Gerhard Wimmer, Vice President of Prime Metals, and Gisa from Metallurgy Specialist at Hedge, and will be moderated by Mike Grant, Global Technology Director at Air Liquide, and me. But now, thanks to the moderators, the speaker, Dr. Sarah Hornby, and IST to make this webinar happen. Please enjoy and spread the word. Thank you very much.
Thank you, Felix. Our first moderator is Nick Aubrey. He is a process engineer in a pyrometallurgy specialty in the sector with Hatch, and his biographical background includes his experience in iron and steel making as a project work focusing on blast furnace iron making, benchmarking, modeling, optimization, and continuous improvement. He has a passion for solving some of the biggest challenges facing iron and steel industry, namely trying to reduce the carbon intensity of iron and steel making. Nick has satisfied his passion by helping clients understand their options to reduce emissions, be it assessing incremental changes to their iron making process or working to understand transformational changes to achieve long-term near zero emission goals. He has a BEng in chemical engineering and management from McMaster University and is a professional engineer in Ontario. Our second moderator is Pollyanna Araujo, a process engineer with WSP Energy in the resource and industry sector. Pollyanna is a process engineer and a licensed professional engineer in Ontario. She also holds a BEng in metallurgical engineering and specializing in steel production, process, plant optimization, and sustainability-driven initiatives. Her expertise includes scrap optimization, focusing on cost reduction through efficient scrap management, and she has worked extensively on electric arc furnace operations, focusing on process optimization including burner profiles to improve thermal efficiency and reduce operational costs. Pollyanna is experienced in secondary refining processes, ensuring steel chemistry consistency for high-quality steel production, and her experience extends to blast furnace operations, where she has worked with both charcoal and coke-based iron-making processes, optimizing, reducing agent ratios for maximum efficiency, and her career reflects a commitment to improving operational efficiency and advancing the steel industry's transition toward a more sustainable future. She is passionate about applying innovative solutions that bridge industries, best practices, and emerging technology. We'd like now to have our moderators present Dr. Sarah Hornby.
Thanks, Charlie. So Sarah Hornby, variously described as a trailblazer and an inspiration for ambitious women, has continually proven nothing is out of reach for women in engineering. She was the first woman to graduate from Sheffield Hallam University with a Bachelor of Science honors in metallurgy. She spent her early career in the UK working for Firth Brown Tools Engineering and British Steel Corporation. Her initial Canadian and US Air Liquide roles, developing new technologies and bringing best available technologies to the metals industry while managing multidisciplinary, multi-location team members, coupled with other electric arc furnace steelmaking optimization positions with Tenova Goodfellow, Midrex, Linde, Intertech, TMS International, put her in good stead to set up her own company, Global Strategic Solutions Incorporated, which supplies expert consultancy and expert witness to the metals and related industries. Sarah holds 5 patents and has authored over 136 international papers, seminars, and courses. She is a fellow of the Institute of Materials, Minerals, and Mining and was their 2022 Hadfield Medal and Prize winner. In 2020, she was a recipient of the AIST Benjamin Fearless Award and the AIST John Bell Award. And in November 2003, she was awarded an honorary doctorate in engineering by Sheffield Hallam University in recognition of her outstanding contribution to engineering in the international steel industry. So with that, I will pass it to Sarah to start the presentation for the webinar.
My apologies. I am suffering dreadfully today with an optical migraine, so I ask you to bear with me whilst we play the video of this presentation, but I will be back live at the end of the presentation to answer any questions that might be given. So with that, hopefully you get all of the volume through also.
Just apologies, Sarah. I think right now there's no volume coming through. I think you might have to reshare your screen there with the sound on.
Wouldn't allow me to click the 2 buttons to get the volume this time. Charlie, it's not allowing the share sound feature.
Is there audio on your machine?
Yes, but it's
Okay.
on fully. But the share sound on the Zoom won't allow me to share.
Our apologies. Let's work this out.
It's not allowing access at all. Now it is.
Yeah, Sarah, try again. I think I fixed it.
Yeah, it appears that it's now available. Thank you.
Very good. Thank you, Madison.
Thanks, Madison.
You're welcome.
I'm Sarah Hornby, and welcome to the AIST TMS 2024 John F. Elliott Lecture, Green Steel Revolution. The lectureship was established in 1950, designed to honor John Frank Elliott, a professor of MIT, for his significant pyro and chemical process metallurgy contributions, acquaint students, engineers, and the public with chemical process metallurgy, its contributions and the exciting opportunities therein, in the hope of inspiring pursuit of careers in this field. Funnily enough, in 1972, he prophesied electricity will become more important as an energy source than it is now, probably not considering CO2 or hydrogen of the future. I'm honored to have been chosen the 2024 lecturer. And fun fact, 50 plus years into a chemical process metallurgy career after I failed my chemistry. Why green steel revolution? Net zero emission steelmaking using fossil fuel energy sources is the definition of green steel that I'm taking. And zero emissions iron making is crucial to the greenhouse gas mitigation. Currently, it's not cost effective with fossil-based fuels. World is currently missing the 1.5 centigrade global warming target, which increased 5 gigatons 2022 over 2021. 34 gigatons came from the combustion of coal, oil, and natural gas. So why the green steel revolution? The 2015 plan is to convert 800-year-old carbon-based blast furnace BOF steelmaking to electrically based 60-year-old EAF steelmaking and make major changes to its operations. Carbon-free electricity, hydrogen-reduced iron, and green carbon and consumables. Increasingly disinterest and inability to comply with the solution is motivating out-of-the-box thinking for iron and steelmaking solutions. Current steelmaking from Zulan 2013, it's a great chart. Blast furnace steelmaking to a BOF, smelt reduction to a BOF, also through a smelter, direct reduction in its various forms, be it shaft, rotary hearth, rotary kiln, or fine ores through the FinMet type process, to an EAF, and scrap 100% to an EAF. As you can see at the bottom here, the 2.2 tons of CO2 per ton of steelmaking drops down to 0.38 when we're looking at EAF steelmaking. And the right-hand globe here is the AIST's interactive module illustrating steel production, which you can access on their website. I'm not going to go through this, but basically I'm showing the amount of carbon interactions in these equations for both the blast furnace and the EAF. So we're very dependent on carbon. The Paris Accord is demanding 0.2 tons of CO2 per ton of steel by 2050, and we're now at about 1.7. The major emissions, as you can see from this table down here, are from the blast furnace at 1.2, secondly from the coke ovens at 0.79, thirdly from the EAF, but it's down at 0.24. The chart here just shows the red blast furnace BOF steelmaking for various countries making over 10 million tons a year. The green is the EAF contributions. And as you can see, China is almost 54% down from 57, but it's also the largest volume of greenhouse gases to the world at 28%. Fact for information, and from this year, the Canadian wildfires last year contributed 647 million tons of CO2, which is 1.22% of the world's generation. It's fourth only to China, India, and the US. And according to them, by 2050, 347 hectares of carbon sink could be lost because of the increasing temperatures. So looking at the IEA's 27 vision and the green challenges, the net zero conversion to 95% hydrogen DRI EAFs by 2070. It's technically feasible, though fraught with challenges, and I'm going to look at those challenges. They are exorbitant in costs and are driving new technology R&D from technology readiness level of 3 to 7, some in less than 3 years. It's the most exciting era since the 60s when continuous casting was developed. Now, green challenge number 1, as I've specified it, is build rates, which I believe are unreachable. Futures predicated on the availability of green hydrogen, energy, carbon, and better qualified scrap. From 1970 to 2020, DRI production averaged at 2 million tons a year. By 2050, it's predicted that we'll need 411 million tons of DRI per year, of which 211 million are hydrogen DRI, requiring 11.5 million tons of hydrogen, 692 terawatts of energy, 1,240 20 megawatt PEMs to create the hydrogen, and 810 EAFs. The supply chain is another issue. Deliveries currently are 106 weeks on transformers post-COVID. Costs, some are 85% up on the pre-COVID costs. Sourcing green hydrogen is the second challenge. It's expensive and there's inadequate supply currently. Linde specified, as you can see on the right-hand side, 252 tons of hydrogen per day is required, 592 megawatts of renewable energy for blast furnace, EAF, and reheat, for 1 million tons of steel only. In 2022, only 0.11 tons of green hydrogen were put on. And in 2023, there were 45 million tons of green hydrogen projects announced for $570 billion of investment. The chart here through the hydrogen map shows both the blue and the green projects in the world. And it's a great source to see what's going on. 2023, there were 1,040 projects. And there's a breakdown there of the front-end engineering and the production efficiency is 50 to 65 kilowatts per kilogram of green hydrogen, which is not very good considering the 100% efficiency would be 39.4. There is a new plasmalysis jet loop ammonia stripping from waste water and manure, which could give us 8 kilowatts per kilogram of hydrogen, which would be fantastic. Other issue is electrolyzer capacity. 71% reduction in cost is required from $1,000 to $1,750 a kilowatt to the $300 to $500 promised. Third challenge is resourcing renewable energy. We, as a steel industry, use 8% of the world energy, and 0.3 to 1 kilograms of CO2 is produced per kilowatt hours, depending on the source. We need 1,437 terawatts by 2050, and that's a $2 trillion investment. There's not enough at the right price. We need a 50% cost reduction. In 2022, 29% was renewable energy. The chart at the right-hand side here shows predominantly all of the energy was basically from fossil fuels. 2023, there was a 0.5 terawatt capacity add, and at 67% energy efficiency, 500 million tons of hydrogen would require almost 19% of the world's total energy. As you can see to the right here, the leading country for renewable energy, of course, is our friends from China. Hydrogen for energy is only going to be 2 to 3% by 2050. And the other issue we need to look at is water. It's been overlooked, and we'll be lacking 30% in our green future. Green challenges 5 and 6 are sourcing carbon and scrap. Historically, iron's been produced from renewables, but with the 20th century came electricity and coal because of deforestation. When the OPEX became 20%, it forced minimization of energy, and we actually, the biomass started to appear, and its use varies by world, as you can see from this graph here, Brazil being the highest user, followed by, funnily enough, the United States, which was quite a surprise. But the cost of processing it reduces world opportunities. The question would be, is there enough biomass? Is it close to the use points? And can we match use to the rate of obtaining? Blast furnace coke replacement is limited because it supports the bed. Kobe Steel has made a phenomenal breakthrough and has the lowest coke in the world at 239 kilograms per ton of hot metal. Arc furnace carbon replacement, it could be inefficient. Injection carbon currently is only 50% efficient, whilst the contained in situ in DRI and pig iron is 95% efficient. Fossil fuel has been required as co-injection with the biomass, which may not lower the carbon footprint very much. My suggestion would be to run the direct reduced plants at 80% hydrogen and maintain the in situ carbon in the DRI. Sourcing scrap, 100% scrap is the lowest emission steelmaking process. But with the recycling of the scrap, there's going to be an increase in the residuals. You can see from the middle chart here that if you're making high-grade auto scrap, you've predominantly got to use DRI, HBI, pig, and the top quality scrap. The prime scrap is dwindling, as you can see here. This is obsolete. It's going to be compounded by the fact that China is going to dump 40 to 500 million tons a year in the next 10 to 20 years of scrap. The other issue is we do not sell scrap to the exacting qualities we do with iron ore. We need to do that. We need to hold the scrap dealers accountable, and we need to pay for quality. Challenge number 7 is zero carbon hydrogen DRI in the EAF, which is inherent when you use 100% hydrogen. The EAFs now, as you can see from the chart here, use 55% electrical and the rest is chemical energy, with carbon being 23%. Carbon foams the slag, gives you a larger surface area. It enables degassing of the melt, nitrogen and hydrogen, increases heat transfer 93%, and tons per hour yield. It also reduces the FeO not only in the DRI but also in the slag, and it doesn't have any ash or volatiles. On the right-hand side here is something that ArcelorMittal put together quite a while ago, showing the increase in productivity, excuse me, the reduction in kilowatt hours, the reduction in electrodes, and the increase in yield to almost 1%. So zero or inefficient carbon is going to reduce chemical energy. It's going to increase the cost and lower the production. It's going to be more gangue. There's going to be more slag to get rid of. There's going to be greater electrode wear. You're going to need double the carbon input to the furnace. And we're going to have to redesign the EAF and the refractories because there will be carbon dissolution with the current system from slag erosion. We're going to have a deeper bath because we're going to need more slag to enable the reactions to occur. And we're going to have to find a better solution for the double slag that's going to be produced. And this is going to be compounded by the dearth of DRI grade ore because of the greater amount of gangue, possibly negating the benefits. Number 8 is sourcing DRI grade ore. Nominally 3 to 4% is DRI quality, which is greater than 67%. In 2021, Australia, Brazil, China, and India mined 73.8% of the world ore, but the quality is deteriorating. Iron's dropped 2%, silica and alumina has increased 2%, and the phosphorus has increased 0.02%. Upgrading some of the ores is very difficult, Pilbara in Western Australia especially, and it's also costly. So the suggestion now is that we redirect the DRI to a SAF, a submerged arc furnace, or OSBF, and then, if we can upscale them, and then put that to either a BOF, EAF, or make pig iron. And you can see that's the chart here to the right, the options. Wimmer from Prime Metals has put this chart together at the bottom. The lighter colors are actually the cost of transformation. The darker cost are the cost of the DRI. And he's showing 67.5% is the break even to go with electric furnace versus OSBF below 67.5%. So obviously some new technologies are required for low grade ores. Electra is iron from ores that can be as low as 30% iron. It's 60-degree temperature, and Nucor is interested in that one. We have Calix that is doing fines recovery from low-grade ore. And Swinburne University and CSIRO are looking at the highly reducible fluxed lime magnetite pellets. And that process would reduce the process to ore, to iron, by a whole step and at a lower temperature. Number 9 is the CCUS, carbon capture, use, or sequestration. Substantially, it's below net zero requirements. 35 global plants only capture 0.12% of the global CO2 currently. The 200 new ones that have been announced are only going to increase it by 0.6%. There are 10 pilots and one-of-a-kind demos, excuse me, that have been funded recently by the DOE in the US. There's a great website here for the IEA, which produces these great charts, and you can change what you want to look at. This looks at the point source, but you can look at project type, region, sector. Iron and steel is the smallest of the installed capacity. Relatively high conversion costs because we need carbon-free hydrogen to chemically stabilize the CO2, and the fixation is limited. Sequestration is also an issue because it's geographically challenged, and it's temporary if no mineralization occurs. They're slated to be the catch-all solution for heavy industry. However, they apparently don't make sense economically, environmentally, or energy-wise. The effectiveness and relevance varies widely across applications, and it's suggested that perhaps worse emissions reduction than it would be from alternative solutions may be appropriate for DRPs. The EU policies are funding a lot of work in this direction, but perhaps at the expense of underfunding more meaningful decarbonization solutions. The other issue is if we can capture it all, how are we going to use it? Who is going to use it? I suggested many, many years ago that we recycle CO2 to the steel mills in place of argon and nitrogen, which would also replace the associated energy. Green challenge number 10 is conversion costs. For the future hydrogen DRI, we need government subsidies, world cooperation, and renewable energy. The 60 projects are shown from the EU on the right-hand side, $91.8 billion of support. DRI costs double with hydrogen. Steel costs triple by the 2030s. We're non-competitive already, as you can see from the bottom right-hand chart, where we're showing Europe versus the US, export for the world, and China. Projects are faltering because FID is negative. There's no instant gratification. They're not meeting promised funding promises. ArcelorMittal Gijon is in feed still because of the hydrogen costs. Germany's waiting for funding. ArcelorMittals have been reported to be 2 years behind because of costs. Algoma has seen a 25% increase in pricing. Blast furnace and BOF revamps and orders are now on parity with DRI and EAF orders, as you can see from the globalenergymonitor.org with the projects. So on to new technology developments. Concurrent with the conversion to hydrogen, DRI, EAF steelmaking, R&D into carbon, electricity and hydrogen and electrolysis have been ongoing. The three circles show those interlapping and specific: biomass, CCU, CCS, hydrogen reduction and production, electricity, and also we need to look at upscaling non-steel old technologies such as SAF, OSPF, and induction furnaces. Challenges appear to be increased energy, scalability, timeliness to market, and the Chinese techno-economic advantage. Best available technology and more applied research at brownfield sites may be used as a stopgap whilst adequate hydrogen and renewable energy sources arrive. New technology developments, are they going to be timely? This is an example of the Finex. The chart on the right-hand side says that they are developing in 15 years only. But if you look at the history, we're looking at 80 years. Again, with Hysarna, 38 years from cyclone to develop a cyclone converter over a smelt reduction furnace. If we look at electric smelting furnaces, excess lean ore and the unsuitability of the resultant DRI for EAF melting have ESFs hailed as the solution. However, we need to upscale them, as you can see in the top chart here. We have circular at 1.1 million tons and rectangular at 1.4 million tons currently. We also need to optimize power intensity, sustainability of the renewable energy and the electrodes, and integrate into the infrastructure that's currently abounds. BlueScope, BHP, and Rio Tinto are exploring these for low-grade Pilbara and medium-grade ores. However, please note, BlueScope is also relining a blast furnace at Port Kembla. Fortescue, Primetals, and Voestalpine are developing a prototype HIFOR furnace at 900 degrees C fluidized bed. They've got a pilot at 1 ton an hour currently running since 2021. They're going to put in a 6 ton an hour demo in Linz by 2027. FID is due this year. Processing all ore types, and it's modular for tonnage. The industrial HIFOR plus a smelter is under MOU with Fortescue for liquid metal production. There's also POSCO's fluidized bed Hyrex, hot hydrogen reduction, ESF DRI melting, and the ESF will replace the Finex's melter gasifier that was. They're going to put a 300,000 ton a year plant in 2028. Commercialization is expected to happen by 2030. Biomass net zero iron making. It's a resurgence on what used to be. Brazil is the largest biomass producer, and they are making ore using charcoal and blast furnaces. They have 88% renewable energy currently. Logistically and graphically, sustainability considerations need to be looked at, matching reactors to supply, and we need to do an emissions life cycle analysis because you need to consider changes in land use and with harvesting versus other opportunities. Carbon neutrality can be achieved, maybe. Red Smelt in Brazil says that they are able to do so with their process. Excuse me. Ferrosilva from Sweden claims that they will actually have a 0.85 ton of CO2 sink per year, and they have the calculations posted. But they're using syngas from forests and agricultural waste, and the biochar and the seal mill and CCU biogenic CO2 is what will give them new products and the sink and they're looking at products of fossil-free ship fuel and biomethanol. There's a pre-study ongoing currently, sponsored by the Swedish, excuse me, and they're designing a 50,000 ton a year DRI plant. They will put it at the Ovaco Highforce plant, using up to 0.9 terawatts of electricity per year and up to 10.5 terawatts of biomass. Another new process with solid DRI is Calix. It's a flash reduction of fines to produce the DRI, multi-patented, pilot tested, and it's 2.5 years since its inception. Processes fines and waste materials, proven to up to 98% metallization with Australian ores, and it up to 1.3 megawatts per ton of HBI, and approximate pricing between $410 to $520 depending on further development. It uses green hydrogen in the renewable energy reactor to produce this zesty green iron and ultimately zesty steel. The hydrogen is only used to reduce the ore, so there's targeting stoichiometry for the hydrogen use. Indirect heating improves the efficiency, lowers the temperature. And there is an ARENA, Australian renewable energy study for 30,000 ton a year demo plant. Zesty steel takes the iron and puts it through a continuous EAF with unpelletized lilac lime, and excess CO2 is scrubbed. And it's offering an opportunity to export value-added DRI HBI from Australia. Shaft furnaces quickly, they're stated at TRL 6 to 8. Hybrid has been producing hydrogen DRI EAF steel at 1 ton of DRI an hour, 5,000 tons a year. It's proved 100 cubic meters of lined rock storage. And they're going to need 120,000 cubic meters when they move to the 1.3 million ton a year demo plant that's going up to be operational by 2026. We also have hydrogen rotary kilns that can run on solar and wind renewable energy sources. There's a 0.5 ton an hour high iron DRI plant in Germany running on 14 megawatts of renewable energy since the first quarter 23. They're going to do a joint venture with Hiron Steel in Namibia with a 15,000 ton a year DRI plant, 20 megawatts of solar to start with at the end of this year. And there's a 2 million ton of DRI per year, ultimately with 18 megawatts of wind and 140 megawatts of solar. CCUs could be appropriate for DRPs if they're proven and upscaled. So electrolytic iron making, there's high and low temperatures. The redox is simple. The iron oxide gives iron at the cathode and oxygen at the anode, and the ores oxide anions are the reducing agents. The high temp process dissolves ore in the molten electrolyte, giving liquid iron, technically faster kinetics, but also much higher capex and opex. ArcelorMittal and others have explored the Mideo Ulcos process from 2004 to 12. Low temperature is solid iron processing, slower rate, lower capex, lower renewable energy, and ArcelorMittal Ciderwin is a demo project at 110 degrees. Boston Metals is the most well-known, I believe, running at less than 2,000 degrees. It's an MIT spin-off. It can process a wide range of ore, but it's limited by the productivity by the cell and current densities in Faraday's law. Critical factors are recarburizing, anode longevity and type, the scaling. It should be noted that they're expecting 400 cells to produce half, and this is an aluminum plant just to demonstrate the number of cells there. 400 cells to produce 500,000 tons a year of steel. So if you put that into a 5 million ton a year plant, you're going to need 4,000 of these in place. There's been a lot of DOE funding, 282 million for the pilot, and the 50 million grant currently to win ultra pure chrome, metal, and high temperature alloys. And commercial, they are already commercial for mine waste in Brazil. and they're expecting steel to be commercial by 2020. A low temperature electrolytic process is Electra in Texas. It's backed by Amazon and Bill Gates, less than 3.5 years from inception. It's converting low-grade iron ore to 99% or higher iron, electrochemically and hydrometallurgically, creating 1 square meter, sorry, I don't know how thick, plate, and they're going to charge that to EAFs with quality scrap. Modular in design, and they reckon 90% reduction in CO2. There's also some Ulcos offshoots, Siderwin with ArcelorMittal I mentioned, Alcowin, which is another ArcelorMittal low temperature, alkaline electrolysis, and alcolysis, which is basically equivalent to our friends Boston Metal. Plasma ion raking is electrode to ore plasma in a conventional furnace with very energetic exothermic hydrogen species which overcome the endothermic hydrogen reactions, enabling efficient redox chemical reactions. Enhanced kinetics, lower temperatures, and there's a pre-pilot demo in the University of Leuven with Voestalpine called SuSteel. Historically, it's been overpriced and failed in the 80s and 90s. We need lower capex and reactor design for the reactor efficiency. Its refractory life needs protection, and we need to have continuous production. Some of the examples are hydrogen plasma red. There's a 100 kilogram scale pilot, which will be then retrofitted to a DC arc furnace. There's an aluminum bauxite waste of 180,000 tons a year, turning into iron making feedstock. And there's I already mentioned the plasmalysis, which technically will strip ammonia from wastewater and manure and allow 8 kilowatt per kilogram of hydrogen production. So brownfield opportunities are the biggest with the blast furnace at 1.2 tons of CO2 per ton of iron, and we're going to anticipate 50% of the ore-based steelmaking still in 2050. So we're seeking best available technology. Improved measurement in the mills will allow us to control what's going on. If we intensify scrap and HBI use, we can increase productivity and reduce coke. And it's shown by IIMA that 7% coke is available for every 10% metallization. And Brooks et al. At Swinburne concur, as you can see from the graph down here at the bottom. Biochar substitution for coke and PCI, what's limited for the coke, as we've already said, because it supports the bed in the furnace. Hydrogen or natural gas injection into the tuyeres can reduce the coke by 9%, alone. Hatch, on the other hand, has said that PCI plus 35 kilograms of 900 degrees C hydrogen can give you a 20% reduction in CO2, but also energy to the mill and 100 kilograms of coke reduction, but it's expensive. If you add top gas recycling and CCUs to this, you can produce an 80% reduction in CO2, which will bring it down to 0.4, which is close to that of an EAF 100% scrap. There's a Japanese course 50 program. They've proven a 30% reduction already with hydrogen, coke oven gas, and CCUs on a 12 cubic meter furnace. They're anticipating they can hit 50% with blast furnace, DRI, and hydrogen. Kobe, as I said already, is down to 239 kilograms of coke. With the BOF, increasing scrap use increases productivity and decreases CO2. Both the charts on the right-hand side here were put together by Swinburne University students using plant data. They show increasing scrap reduces heat loss. So for 35% scrap, you're going to have a heat loss that's less than 0.9%. If you drop down to 10%, then you're looking at a heat loss that's high at 6.75. You're going to require smaller scrap, preheated and continuously fed, probably. Increasing PCR on the bottom from 10 to 30%. You can see an increase in scrap from 22 to 28% on the dotted line, and global warming potential drops by 10%. These two charts basically show HBI and the BOF as greater cooling intensity and productivity than you have with scrap. EAF's green energy is the key, followed by scrap quality. Renewable energy would have saved 212 million tons of CO2 in 2023 if it had been available. 100% scrap melting, as you can see on the right-hand side here, will give us 0.18 tons of CO2. If we beneficiate scrap, maximize its use, and avoid using the DRI, HBIs of the world or base metallics, then we're going to have a much lower CO2 count. If we shred our scrap in-house, improve quality and density and yield, then we will also have the added benefit of fluff sales, which is non-ferrous and definitely profitable. We also need continuous analysis in the plant. We need to develop residual and sensitive steel grades because the residuals are going to increase with continuous recycling and more obsolete scrap coming on the market, as we said already. If we preheat the combustion air, we can reduce the kilowatts and the meltdown time. If we substitute hydrogen for natural gas in the oxy-fuel burners, we can save more CO2. And if we look at putting on value in use of materials with off-gas analysis and heavy control of the EAF, we can maintain lower cost steel. If we look now quickly at the industry status, Europe is ahead because they are forced, with lack of natural gas controlled by Russia, to look at opportunities to reduce their 70% blast furnace steelmaking and go green. Here's the project for 60 projects I mentioned earlier, and I'm not going through specifics. The industry status can also be seen on the globalenergymonitor.org. It produces these maps, and you can see from the left-hand side, it's quoting 1,163 iron plants, various concoctions, electric, blast furnace, iron making integrated. On the right-hand side, you can dial in what steelmaking method you want to look at, and whether you want to look at announced, construction, operating, mothballed, retired, cancelled, or operating pre-retirement. If you go to one of these circles with a number in it, it's showing multiple plants at that site, and you can explode them. And then you can drill down, as I did here with Soldana Steel, into specifics of the plant, and then you can go even further down to see what's happening. This is a summary which basically says that the integrated blast furnace DRI and the iron making DRI blast furnace are project numbers for the A and C, which is the announced and construction, are pretty equivalent. And the right-hand side is the prime metals forecast showing steel production will shift, but we're still going to have 0.75 billion tons of blast furnace BOF steelmaking in 2050. I'm not going to go through the international solution, the decoupling, but basically we're going to have variation across the world in availability of energy, iron ore, hydrogen, CCUs, feasibility, and the iron ore map there showing Brazil, Africa, Middle East, and Australia. But we need to consider that. There's committed green steel installations here. I also will not go through this. I will let you have a copy of the report to read it. But there's some substantial startups coming in up to 2025 and 27. So in summary, the scale of progress and investment falls short of the required 1.5 degrees C global warming need. Hydrogen DRI EAF steelmaking is technically viable, but challenged with build rates, availability of green consumables, and predominantly conversion costs and the FID failings. We've got a catch-22 situation. We need to guarantee the cost of low carbon energy and hydrogen, but conversely, those who make them need to see the demand. We need to decouple iron and steel making, sort of ore and iron making with renewable energy and steel making, and we still need the blast furnace pig iron. In the meantime, we need to look at black steel taxes for non-compliant nations, best available technology and applied research and development of brownfield sites as a more techno-economic solution and stopgap, And the green steel revolution has spawned innovation and new technologies. Questions do remain. Innovation to market and build rates, can they be sped up? Can the CCUs truly be a long-term fix for the steel industry? And also, can we improve the hydrogen efficiency and volumes and cost? So there are major career opportunities which exist to further this green steel revolution. And I think it's an exciting time to be in the industry. Part of me regrets that I'm at the end of my career. I hope you will consider a career in this great industry. I thank you for your attention. If you have any questions, please ask. And if we don't get to them, please contact me through my email that's posted there. And I thank you for your attention.
Thank you, Dr. Hornby. We will now turn to questions by both moderators. And Sarah, you can be ready for the questions that come audibly, as well as answering questions from those submitted during this process.
Okay, thank you.
Yeah, I'll just reiterate the thanks, Sarah. That was a great presentation. But with the time, I'll just get right into the questions. So this one's actually from an anonymous attendee, and they said, great presentation. They were wondering, what is your opinion on Boston Metals and Electra around technology maturity, and also on scale up? Would their rate of production be able to significantly help decarbonize the steel industry?
My personal opinion is that with the Boston Metals and the number of batch process plants that will have to be input for even 1 million tons a year, that it's going to be difficult to persuade the steel industry to operate that way, I think. They got rid of the open hearths that were batch that had to be tapped as a batch, and looking at 400 units to tap to get that tonnage, I think it's going to be a challenge. Technologically, they've still got a lot of issues to solve, the voltage, the electrodes. I hear that they are on track to do so, but I haven't seen any results to say that they've achieved the 5 volts. Electra, I don't know how far they've got. The last I heard, there was no specific thickness to the plates that they were producing. I think it's possibly both of them will be good for niche markets where there's a small requirement.
Okay, so second question from Ram Mohan. He said, excellent presentation. Which projects and technologies in the world, according to you, has greatest potential to help us decarbonize in the industry? I understand there is no one solution fit all, but the most promising. Thank you.
I've been a proponent of looking at how we can beneficiate the blast furnaces for a long time, because there's so much impact if we don't maintain some kind of blast furnace type steelmaking in terms of the personal aspects of steelmaking and the number of people involved. There are a few new projects coming. One of the ones I mentioned was Calix. It's a low footprint. It's not got very much complicated equipment, and it appears that it can deal with some of the lower grade materials. But again, it probably is going to be a 30 to 50,000 ton a year individual units, so it would be multiple units that would be required. And the ESF, hopefully that can be upgraded and used for iron making, steel making, iron making, so that they can combine the low grade ores through the DRI, through the ESF. Hopefully that will prove to be the case, but it's going to take a few years, obviously, because they're just starting to work on the ESFs.
That's great.
Lots of room for improvement.
Yep. Oh, definitely. The next question comes from David Marshall, and he also reiterated it was a great presentation. His question is around time versus risk. It's when will enough of the known and unknown risks and expected scaling limits be proven for a lot of these technologies so that FEL1 project investments of $1 billion can start to be improved? And he's specified like order of magnitude, like 2030, 2040, 2050, like rough timeline in your opinion of de-risking these.
Well, this video was put together last August, and even since I gave the last lecture in December, things have changed significantly. I understand the Dofasco project is now canned permanently. There's a lot of talk in Europe that the conversion to electric furnaces has been delayed. There is gas coming now from Russia to Germany, at least, and some of the other European countries. Everyone's backpedaling because of the cost, the uncertainty, the inability to reach the renewable energy and hydrogen that is required for any of this work. It's even questionable whether there will be enough hydrogen to use to inject into the blast furnaces. So I think that the declarations for 2030 are going to be at least 10 years delayed, at least. And one of the big problems is, as I said, people are promising funding, but when it comes to the FIDs, they're not being put through. Maybe 20, 25% the investment decisions are going ahead. So it's a huge cost for everybody involved.
One question from Ahmed. If using blast furnace grade pellets, what would be most common sense process route without a blast furnace? So what to do with the blast furnace pellets that is only for blast furnace if you're not using blast furnace?
Well, the DRI plants can take pretty much any quality into them. So whether it's blast furnace or DRI quality, the DRI quality basically refers to whether or not the DRI can be then processed through the electric furnace, not whether it can be processed through a DRI plant. So the obvious solution, if the ESFs work, will be put the blast furnace grade pellets into a DRI plant, which is going to be run with hydrogen and hopefully not at 100%, and then put that to the ESF if they can make that work, or to some smelter process, and then take it from there either to the BOF, which would be technically the least cost scenario, or through into the electric furnace as either pig or liquid.
Charlie, do we have time for any more questions, or do we gotta wrap it up?
Nick, I believe that we're at the top of the hour.
Yep.
We have a few more sign-off slides, and we'd be glad to continue the conversation with Dr. Hornby directly. Thank you again, Sarah. We certainly appreciate the expanse of this knowledge and sharing it with us.
Thank you, and I'm sorry there was such a challenge at the beginning.
Well, it was worth the wait. Thanks.
Great, thanks.
So we'll leave it to you, Charlie, to sign us off.
AIST would like to remind you, you can find these recorded webinars under the conference and exposition portion of our website with a drop-down that's specifically for webinars. This one shows the previous webinar in its production stage. Each new webinar will come on this page as it comes up. The URL at the top of the page also indicates that there's a large amount of information on new activity within the subcommittee, and that's beneath Judy Lee's presentation at an area that says additional resources. We also have close to 10,000 written manuscripts, papers, presentations, seminars, output of the seminars in our AIST Resource Center, and we encourage you to go there for download of specific items. The upcoming training has now begun, the project management in Fort Worth, and the modern electric furnace steelmaking taking place in person now this week. In another week, we have the long products training course in Fort Wayne, Indiana. And the rest of these are available at the URL above. It's the fastest go-to site for all the calendar activities that are scheduled by AIST. Of course, we'd like to sign off with everybody looking forward to AIST Tech, our large annual meeting each year, this year in Nashville, Tennessee, and the dates 5 through 8 of May. Thank you all for attending. Please come back to the recording once it's available, and look forward, as Felix mentioned, to the additional webinars in the future. Thank you all. Have a good day.